continuing on with rotational motion, remember what we talked about last time, that a net torque causes an angular acceleration. Some of our torques, if there is a net one, is equal to I times alpha, where again, tau is for torque, I is the moment of inertia, and alpha is the angular acceleration of whatever object it is that you're exerting a torque on. Okay? This, again, is directly analogous to Newton's second law for linear motion. You have a net something that is causing behavior, this being the cause, and the effect being the actual linear acceleration. And the mass being the resistance to motion, the resistance to change in motion of this situation. So the heavier, the more mass something has, then the more it's going to resist some change in acceleration for a given force. So, well, some change in motion for a given force. Just like for something that has a higher moment of inertia, okay, then it's going to have a larger resistance to motion for any given torque. Okay. So that is the quantity that, well, it quantifies the resistance to the change in motion. For this, the change in linear velocity. For this, the change in angular velocity. So when we have to look at our conditions now for what is going on, we have to use Newton's second law, and we have to use, for forces, and we also have to look at the sum of the torques. So if we have, say, like we did in class, an Atwood machine, which is just two blocks on a pulley, basically, then we no longer can neglect the fact that the pulley is turning, and the fact that forces have to be applied to this pulley in certain ways to create a torque that ends up making it go in a certain direction. So if this tension that it is experiencing is bigger than this tension, then it will move to the right. If this tension is bigger than this one, it will move to the left. So the free body diagrams for these, like we did in class, would be the tension up for each of these two, and then for the pulley, you'd have the tension down on each side from the two parts of the rope. And if one of these is bigger than the other, it'll turn. If they're equal, then it won't turn. And so that is what you'll have to be thinking about if you're analyzing a situation where something is experiencing an angular acceleration. If something is moving rotationally like this, then it has an energy associated with that. So the thing I said in class, I mentioned, was that if you have a yo-yo and you make it sleep, where it stays at the bottom and it keeps spinning, it still has energy associated with that. It's just not moving side to side or up or down or front to back. So kinetic energy, we've talked about, is when it's moving side to side, up or down or front to back, and that's called translational kinetic energy, when it moves in those regular coordinates. However, there is rotational kinetic energy too, which it has from just spinning. So there are two types of kinetic energies now. We have kinetic energy translationally, meaning moving side to side, front to back, or up or down, which we'll call Ke sub t. And then we have the kinetic energy from something spinning, because it actually is rotating around. So a ball that's moving across the floor has a rolling motion associated with it, and also the fact that it's moving this way. So it has two different types of energy. It has the translational, that overall is making it go to the right, and it has the energy associated with it rolling, with it rotating like this. And the translational, as we know well by now, is 1/2 mv squared. And so in order to take this into the angular analog, like we've been doing, with force equals ma and torque equals I alpha, the analog for mass is our moment of inertia. And the analog for our velocity is our angular velocity. And so the rotational kinetic energy is 1/2 I omega squared. Okay. Now, how do we directly relate these? Let me show you that quickly. That if I'm looking at a ball rolling, I want to look at the kinetic energy of each little piece as it goes around. So I break that up into chunks of different parts of the mass at different radii from the center of rotation. And so I have that the kinetic energy is equal to the sum of all the 1/2 mv squareds, where we're specifically looking at the tangential velocity of each piece. Okay, so the ball is rolling. We look at this part, it's moving that way. If we look at this little bit on the inside, it's moving that way. This little bit is moving that way. That's what we're talking about with regard to the VT that's involved. Okay, the tangential velocity. And we know how to relate that tangential velocity to the angular velocity that we've been describing, where Vt is equal to the radius of our object, or how far that thing is from the center, times the angular velocity. And so that's going to be equaling 1/2 m times r squared omega squared. If that object is a rigid body, then the omega is going to be the same for all different parts. Okay, it's going to be transcribing the same angle for all parts, no matter how far you are from the center. But of course, your distance from the center does change, so that r is still an r, but I can bring that outside of the sum. Okay, technically I should have put down i's for I equals 1 to n, talking about every single piece on here. So this would be I, that would be I, but I can bring that omega out because it's constant for all. So what that means is that I now have 1/2, bringing the sum inside, the sum of mi ri squared times omega squared. So the sum was only acting on this part, but we know this to be the definition of I. So this is our moment of inertia. So we have 1/2 I omega squared. Now why is this important? Well, we have two different kinetic energies to associate here, which means that we can relate this to the other energies we've been talking about, that being the potential energies and the work. So, our work energy theorem, where we just had WNC is equal to delta KE plus delta PE, now we have parts that make up the PE and parts that make up the KE. So specifically, this is going to be delta KE translational plus delta KE rotational plus delta PE from gravity plus delta PE if there's a spring involved. So we could theoretically have all of these involved. So you could have a ball rolling down a hill that ends up hitting a spring. And so then you would have all of these 4 different things involved, and if there's friction on that hill that is rolling down, then the WNC is non-zero. And we can completely describe our situation based on all those different aspects of it. And of course, if there is no friction, this side is 0, and what that says is that the energy before equals the energy after. So any kinetic energy translational, rotational, or potential energy, gravity, or spring before has to equal those 4 things after. And so you can characterize all the energy situations now as long as you include both of those things, allowing for the object to rotate. So the other portion we mentioned today was the angular momentum. And I'm going to bring you back to the definition of linear momentum, where linear momentum is equal to an object's mass times its velocity. And talking about the characterization of what force is in terms of momentum means that the sum of our forces is equal to a change in momentum with respect to time. So that comes from ma, where ma is also m delta v over t. And so m delta v is your delta p, your change in p. So a net force will cause a change in linear momentum. Let's look at the torques now. If we know that the sum of our torques is equal to I times alpha, well, alpha, as an angular analog to the linear velocities, is equal to the change in angular velocity with respect to time. So this is I delta omega delta t. So now we have, instead of m delta v, we have I delta omega. So we have something that's an I omega final minus an I omega initial over I delta t. And we call that I omega L. It's given the letter capital L. So the angular momentum then, which is the angular analog to our linear momentum, is L, which is our moment of inertia times our angular velocity. So that means that the sum of our torques is equal to delta L over delta T. In this situation, where the sum of our forces is equal to delta P over delta T, if we have no net force, that means there's no change in P with respect to time, or linear momentum is conserved. Now, if we have no net torque, then that means that 0 is equal to delta L over delta T, which means that angular momentum is conserved. And so, we can characterize that by the I omega, but let me write this down. So sum of our torques is equal to delta L over delta T. If this is 0, then that means angular momentum is conserved. Okay? Or I omega before equals I omega after. I'll write it in terms of my usual notation. I omega initial equals I omega final. Okay, so if you change one of them, you're going to have to change the other. So this is the classic ice skater example, where if you have a situation where someone is spread out, so their moment of inertia goes, moment of inertia is larger than if they're constrained like this, because R is smaller here than it is here. If you change your moment of inertia from being large to being small, then that means that your slow angular velocity you had here is going to actually be larger, because you've changed your I. And so if I omega before has to equal I omega after, then the slow speed ends up being a fast angular speed instead. So just starting out slow and coming in together will change your moment of inertia, and therefore, in order to conserve angular momentum, your angular velocity has to increase. Now, of course, if you have friction involved, that's going to take stuff away, and so things are going to be completely conserved. But this is the idea that there's no net torque involved, then you end up with conservation of angular momentum. So we can characterize now the rotational kinetic energy, where again KE(R) is equal to 1/2 I omega squared, and the sum of our torques is equal to delta L over delta T, meaning our angular momentum of L equals I omega, and now our conservation of angular momentum, meaning that I omega before is equal to I omega after if you don't have an external net torque.